So today you're going to take a look at a few examples of problems of circuits, AC circuits, wherein you are going to apply the concept of phasors. Okay, dun sa tatlong problems na ito, okay, sinolve yung voltages and currents, voltages across each circuit element and currents through each of the circuit elements. And finally, ginawa yung impedance phasor. Gagawin yung impedance phasor diagram. Okay, so yun yung makikita niyo sa tatlong examples. As in previous meeting, okay, towards the end, when you scroll down itong slide na ito, you'll find this list of problems. Okay, and makikita niyo rito na instead of yung exercise number, ang nakalagay dito ay yung figure number. Okay, so you have to go to the reference material and take a look at the figures. And what you're going to do is to select one of these problems. And sa figure na masaselect ninyo, alamin nyo kung ano yung voltage and current, voltage across each circuit elements and currents through each of the circuit elements. And finally, gagawin nyo rin, i-draw nyo rin yung impedance phasor diagram. You need to draw the phasor diagram as accurately as possible. So you may use MATLAB, or if you like, you can get a graphing paper and then use anong tawag dito? Protractor. Okay? Kung maghahanap kayo ng graphing paper, magpaalam lang kayo sa office, and dun sa drawer ko, dun sa wooden table, sa drawer na yon, merong mga graphing paper dun. So just get one. Feel free to just get one sheet of graphing paper para ma-plot nyo ng maayos yung impedance phasor diagram ninyo. As in the previous exercise, submit your solution via VLE or in a designated Google Drive folder. Okay. Then, once you have made a submission, saka nyo lang isusulat yung pangalan ninyo next to the problem that you have made a submission to. Okay. The deadline is today, 6 p.m. Okay, and there will be no extensions. Okay, so here are the three examples for today.
Okay, so we have this circuit, and you see there are no instructions, and basically what we would like to do is to simplify this circuit into its equivalent impedance, and then from the equivalent impedance we can get the current and also get the phasor diagram of the equivalent circuit. So the given quantities are a sinusoidal voltage of 10 volts operating at 2.5 kilohertz. You have two capacitors C1 and C2, and then three resistors R1, R2, R3, and R4. R4 and C2 are parallel to each other. R1, R2, R3 are in series, and they are also in series with C1. So the first thing that we need to do here to simplify this circuit is to get the equivalent circuit for the parallel R4 and C2 circuit elements, and then from there combine them with the C1, R1, R2, R3 to get the total equivalent impedance. Okay, so the first step that we're going to do is to determine the angular frequency. So the angular frequency in this case is 2 pi f, and f is 2.5 kilohertz, so that's 5,000 pi hertz, which is about 1.57 times 10 to the 4. Which is about 15.7 hertz, kilohertz. Okay. Okay, the next step is to combine these. The next step is to combine these two parallel circuits, and what we want to do with that is to get the equivalent impedance, which we will call C1. So in this case, so combine C2 and R4 to get Z1. So to get Z1, we first need to get Y1, but to get Y1, we need to get its components, G1, the conductance, and the capacitive susceptance. So the conductance G4 is just the reciprocal 1 over R4, and the capacitive susceptance BC2 is just the reciprocal of 1 over XC2, which is just omega C2. Okay, so once we have that, we get Y4 equals G4 minus or plus BL minus BC2. Sorry, that's minus. So So now we can solve for y4, which is equal to g4. This will give us, wait. So now we can solve for y4, which is equal to g4 minus bl minus bc2 and j hat. Okay, this will then give us a value of 1.1 millisiemens plus 0.7 millisiemens j hat. Okay, now I used MATLAB in order to solve for these quantities so that it will become easier. The next step is to solve for Z4 or Z1, which is the reciprocal of Y4. Okay, now if you're not familiar with handling complex numbers, this is how you how you solve for it. So let's say if you have a complex number of 6 plus 4j, and let's call that a. Okay, and if we want to get b, which is 1 over a, okay, what we do is we take the reciprocal of 6 plus 4j. Okay, and to remove the complex number in the denominator, we multiply everything by 6 minus 4j. Okay. Okay, and what we will get for b is 6 minus 4j divided by 6 squared plus 4 squared, because 6 squared here and 4 squared there. So if you're not familiar with using complex numbers, okay, this is what you can do. So let's say we have a complex number a, which is equal to a real plus its no. Let's say we have a complex number which is equal to a times a cosine theta, because this is the real component, plus a sine theta, which is the imaginary component. Okay, and then we want to take the reciprocal of that number, which we equate to b, for example. What we're going to do then is write this down in the denominator. Okay, and then we multiply everything by 1, or a cosine theta minus a sine theta j divided by a cosine theta minus a sine theta j. Okay, the numerator becomes a cosine theta minus a sine theta j, everything divided by a squared cosine squared theta plus a squared sine squared theta. And it's a plus sign here because j squared, as we know, is -1. So we factor out the a in the denominator, a squared in the denominator. We're left with cosine squared theta plus sine squared theta, and that should be equal to 1. So the denominator is a squared, and then we can simplify this as, sorry, we can then simplify this as cosine theta over a minus sine theta over aj. Okay, now remember that a here is the amplitude, so just to be clear that that's the amplitude and not the phasor component, which means that this will give us, or you can compute manually using this equation, or using this technique, or you can simply use MATLAB. So in MATLAB, Z1 will give us 627 ohms minus 421 ohms J hat. Okay, now that we've solved for Z1, okay, this is the equivalent circuit there. Next step will be to solve for R1, R2, and R3. So in that case, okay, that's the step 2. Simplify R1, R2, and R3. So let's say that's R4. So R1 plus R2 plus R3 is equal to R4, and this will give us about 2.68 kilo ohm. Okay, so we call this as our R4. Okay, next we combine this C1 and R4 to get the impedance Z2. Okay, and that's actually easily done. Okay, what we do is simply to write Z2 equal to 2.68 kilo ohms plus XC, which is 1 over omega C. So 1 over omega C J. Sorry, this should be minus, because recall the equation is Z2 plus, or Z2 is equal to R plus XL minus XC J hat. Okay, so this should have a minus sign. So Z2 for us will be equal to 2.68 kilo ohms minus 4.24 kilo ohms J hat. Okay, so now that we know Z1 and Z2, we can combine them to get the total impedance, or the equivalent impedance. So the equivalent impedance will be, you call z, so z1 plus z2. Okay, and that's also easily done. We only add up the real numbers together and then the complex number, the imaginary numbers together, and what we get is 3.331 kilo ohm, then minus 4.67 kilo ohm J hat, and that's for Z. Okay, so we need to get the absolute value of Z, because we want to get that. We want to get that because we're going to use that value in order to solve for the current I. So this is 5.72 kilo ohms. How did we get this? 3.31 kilo ohms squared plus negative 4.67 kilo ohms squared, and you take the square root of that. Okay, so that's your Z. Okay, and for the phase angle, okay, now remember that the phase angle is equal to tangent inverse of XL minus XC divided by R. Okay, this is our R and this is our XC. Okay, so that will give us a value of negative 54.7 degrees. Okay, so now that we have solved for this, we can now draw the phasor diagram. Okay, the phasor diagram for the impedance involves the real component, which is this value, the imaginary component, which is this value, and the amplitude, which is this value. Oh, a solution appeared. The magic of technology. Okay, so here we have the impedance phasor diagram. The x-axis is the real axis. As you can see, it's about 3.31 kilo ohms. Okay, so this is actually in units of ohms. And the y-axis is the reactive component, and it's about 4.67 kilo ohms. Okay, so this is in unit of ohm. Okay, you don't see that it's actually 3.31, so it's 3.5 here, and here it's 4.67, but it's supposed to be 4.67, but you see 4.5 here. And the reason for that is that in MATLAB I'm using a command called quiver, and quiver draws a vector, but it does not draw the whole magnitude of the vector. Because graphically you draw multiple vectors and you don't want all those vectors to touch from head to tail. So this is why the length of the arrow does not correspond to 3.31 or 4.67 as it should be, and that's only because MATLAB or the command quiver does not draw the arrow to its full magnitude. Okay, but you can check for yourself that the mathematical answer is correct. You can also see that the angle is negative 54.7 degrees, And it's negative because, again, the circuit is purely capacitive, and we expect the reactive component to be in the negative part. Okay, the magnitude of this green arrow is 5.72 kilo ohms. Okay, there's one more thing that we need to compute, and that is the current. So the current, okay, we can easily get from by solving by dividing the current. We can easily get by dividing the voltage with the absolute value of the impedance. And the current here in this case will be V sub S divided by the absolute value of Z. So this is 10 volts divided by 5.72 kilo ohms, okay, which is about 1.7 milliamperes. Okay, now let's try to solve this circuit, okay, which includes a voltage source and an inductor and a resistor, a set of inductor and a set of resistors. The voltage source is 18 volts and the frequency is 80 kilohertz. We have three resistors R1, R2, and R3, and two inductors L1 and L2. Okay, and the first thing that we can do here is to solve for omega, which is equal to 2 pi f, okay, which is equal to 480, 160,000 pi hertz, which will be equal to 503 kilohertz. Okay, now that we know that, the next step is to simplify our first circuit, which is this one. These two are in series, and we are going to solve for the equivalent admittance Y1, but in order to do that, we also need the equivalent inductance, equivalent impedance, okay, which is Z1. So Y1 is just equal to Z1. Okay, so first, let's solve. So let's combine R3 and L2. Okay, since R3 is a real value, then L2 is part of a complex. Now is the complex component of Z1. Then we can write Z1 is equal to R3 plus omega L2J. Okay, and Z1 is easily solved as 5.6 kilo ohms plus 4.02 kilo ohms J hat. Okay, let's get the absolute value of Z1. Z1 is 6.89 kilo ohms, and its phase angle, okay, which is equal to, if you recall, XC minus XL over R, where XL is just here 4.02 kilo ohms. So this will give us 35.7 degrees. Okay, so now we can get Y1, okay, and this is the reciprocal of Z1, and we already know how to solve it from the previous problem. So this is the absolute value of cosine theta over the absolute value of Z1 minus sine theta over the absolute value of Z1 J hat. So from there we can get Y1 to have a real and imaginary components of 0.118 millisiemens minus 0.0846 millisiemens J hat. Okay, so this is our Y1, and we can also solve for this corresponding admittance, and this is quite simple because there's no complex component. So number 2, we solve for the corresponding admittance of R2. So solve for Y2. So let's say Y2 is equal to G2 divided by 1 over R2. And Y2 is just equal to 0.303 millisiemens. Okay, now that we have these two, okay, we can then combine them, okay, to get Y3. Okay, so we now solve for Y3, and Y3 is just the sum of these two admittances. Okay, so Y1 has a real component and Y2 is just a real component, so we just add that, and then Y3 will only get the real component or the complex or the imaginary component from Y1. So Y3 is equal to 0.421 millisiemens minus 0.0846 millisiemens J. Okay, so now that we have solved for Y3, the next step is to combine that with L1, but Y3 is a reciprocal. So but we cannot combine Y3 with L1. We need to convert Y3 into Z3. Okay, so what we need to do actually is to solve for the impedance Z3, because Z3 is in series with L1. So Z3 is equal to 1 over Y3. Okay, and again, we already know how to do this. Just get the real component of Y3 and the phase angle, and then use this same equation here. So Z3 will give us so the next thing that we need to do is to solve for Z3, or let's say Z2 instead, because we don't have Z2 yet. Z2 is just the reciprocal of Y3, and we already know how to do that simply by using this equation here. Okay, so just to complete the procedure, we need to get Z2, which is equal to 1 over Y3. So Z2 is equal to 2.28 kilo ohms plus 4.59 kilo ohms J hat. Okay. Now we can combine Z2 with L1 because Z2 is in series with L1. You cannot combine Y3 with L1 because Y3 is the admittance, and it's solved by getting the parallel, or by solving for the equivalent parallel circuit. So Z2, okay, we combine with L1 by doing this. We get Z3, okay. So just to complete solve for Z3, so we get Z3 equal to Z2 plus omega L1 j hat. Okay, and then we get Z3, okay, which is combination of this. So this is Z3, okay, and Z3 will have a value of 2.28 kilo ohms plus 5.49 kilo ohms J hat. Okay, now again, Z3 is an impedance that was solved using a series circuit, but this equivalent circuit is in parallel with R1, so we need to get the reciprocal of Z3 first, okay, in order to solve for the equivalent of Z3 with R1. Okay, so what we are going to do next is to get Z3, or Y4, which is the reciprocal of Z3, okay, and then combine that with Y5, which is the reciprocal of R1. Okay, so simplify. The next step is 5. Simplify R1 and Z3. So to do that, we need to get Y4, which is the reciprocal of Z3, and that's easily solved to be 0.065 millisiemens minus 0.155 millisiemens J, and then Y5 is nothing but 1 over R1, okay, which is equal to 0.833 millisiemens. And then we get the Y total to be equal to 0.898 millisiemens minus 0.155 millisiemens J hat. And finally, we can get the equivalent impedance, okay, by taking the reciprocal of Y total. So this will be equal to 1.08 kilo ohms plus 187 ohms J hat. The absolute value of Z total is equal to 1.097 kilo ohms, and its phase angle is equal to 9.82 degrees. Okay, and just for completion, let's solve for the current. So the current is equal to V sub S, okay, divided by Z total. V sub S here is 18 volts and Z total is 1.097 kilo ohms. So the current is 16.4 milliamperes. Okay. If we do all of this in MATLAB, we can immediately solve for the phasor diagram of the circuit, the equivalent phasor diagram of the circuit. So again, this is the real component, and this is in ohms. The imaginary component is also in ohms. Okay, we see that Z has a total of 1080 kilo ohms, and here the complex or the imaginary value is about 1.87 ohms. So uh, the the absolute value of z, or the magnitude of z, can easily be computed to be the magnitude of z can easily be computed to be about 1100 kilo ohms. Okay, now this problem involves a combination of resistor, inductor, and capacitor in series and in parallel. The voltage source here is 10 volts. It doesn't have a frequency because, as you can see, the capacitive reactance is already expressed in terms of kilo ohms, and the inductive reactances are already expressed also in kilo ohms. So it's no longer necessary uh, to determine the angular frequency because of this. So which makes our life a bit easier. So the first thing that we need to do, okay, is to combine these three circuit elements that are parallel to each other. And in order to do that, we need to, so let's write it down here, combine XL1, XL2, and R2. In order to do that, we need to take the reciprocals of each of these and then combine them, which means that we need to take the conductive reactance, conductivity. We need to take the conductance G2, which is 1 over R2. We need to take the inductive susceptance BL1, which is 1 over XL1, and the second inductive susceptance, which is BL2, is equal to 1 over XL2. Okay, and from there we can already get the admittance, the equivalent admittance, which you call in this case as Y1. So Y1 is equal to G2 minus BL1 plus BL2 J hat. And we have a minus sign here because the taking the reciprocals means that J becomes 1 over J becomes negative J. Okay, so when we do that, again, you can do that in MATLAB if you wish. So we have 0.100 millisiemens minus 0.300 millisiemens J. So that's our Y1. Okay, and in order to combine that with R1 and XC, we need to take the reciprocal of Y1. So the next step is to take Z1, okay, which is the reciprocal of Y1. Okay, and we already know how to do this. We need to get the absolute value of Y1, and we also need to get the phase angle of Y1. Okay, and Z1 will give us 1 kilo ohm and plus 3 kilo ohms J hat. Okay, now that we've done that, okay, we can then combine that with R1 and XC. So combine R1, XC, and Z1. Okay, so this will give us our total impedance, the equivalent impedance. Okay, this is then equal to R1 minus XCJ hat. Okay, why is that a minus sign? Recall that Z is equal to R plus XL minus XCJ. Okay. And that is why we have a minus sign there. And then simply we add this with Z1. So Z total will give us 4.3 kilo ohms plus 2 kilo ohms J hat. Okay, just for completion, we can write it like this: XC is equal to 1 over C. Oh, but we already know XC. Okay, so once we know, well, now that we've combined everything, okay, so this is now our Z total. Okay. Okay, we can get the amplitude of the Z total, of course. And that's 4.74 kilo ohms. You can also get the phase angle. And that's 24.9 degrees. Okay, now in this case, we won't draw the phasor diagram, but instead, let's try to solve for the values of the voltages across each circuit element and the currents across each circuit element. We know that R1 and XC are in series, and that is also in series with Z1, which is the reciprocal of Y1. Okay, so this means that Z1, R1, and XC are or have the same currents. So solve for current IR1 and the current IC, okay, which will also give us the current across Z1. Okay, now how do we do that? Well, very simply, I is equal to 10 volts divided by Z total. Okay, and by doing that, we get 2.1 milliamperes. Okay, which means that the current across R1 is equal to the current across C, which is 2.1 milliamperes, and this is the current across the impedance, the equivalent impedance Z1. Okay, so that's the current through here, and here just before it reaches the junction. Now that 2.1 milliamperes will be distributed along these lines, and that's what we're going to solve for next. So what about voltages? Voltages across R1, XC, and Z1. Okay. So the voltage, so the voltages, okay, so VR1, VC, and VZ1. So the voltage across R1 is just equal to the current that we have computed, and the resistance, which is 3.3 kilo ohms, and that gives us 6.96 volts. The voltage across the capacitor is 2.1 milliamperes times 1 kilo ohm. This will give us 2.11 volts. And the voltage across Z1 is equal to 2.1 milliamperes times 3.16 kilo ohms, which is 6.67 volts. Okay, how do we get 3.16 kilo ohms? Well, we simply take the absolute value of Z1, and that will give us 3.16 kilo ohms. Okay. Okay, so notice that it doesn't add up to 10 volts. So it's not 10 volts. And why is that? Remember that we're dealing with phasors, so this is not the correct way to check if you have the correct answer. The correct way is to solve solve this by taking the sum of the squares. So VR1 squared plus VC squared plus VZ1 squared. And if you do that, you get around 9.9 volts. Okay, so that's approximate, and that's all just because of rounding off errors. Okay, now VZ1 is the voltage across the equivalent impedance Z1. But the equivalent impedance Z1 was obtained by taking the equivalent, or by taking XL1, XL2, and R2 in parallel, which means that the voltage across these elements here is the same as the voltage at Z1. So that's 6.67. So in other words, so voltage across L1, voltage across L2, and voltage across R2. So voltage across L1 is equal to voltage across L2, voltage across R2 is equal to voltage across Z1, which is 6.67 volts, because they are in parallel. Okay, and we can easily get the current then. So we can get the current through L1, L2, and across R2. So IL1 is equal to VZ1 over XL1, which is 6.67 volts divided by XL1, which is 5 kilo ohms. So this is 1.3 milliamperes. Then IL2 is equal to VZ1 divided by XL2. So 6.67 volts divided by XL2, which is 10 kilo ohms. So this is 0.67 milliamperes. Finally, the current across the resistor is VZ1 divided by R2, which is 6.67 volts, divided by R2, which is also 10 kilo ohms. So that's 0.67 milliamperes.